This video is based upon a paper presentation that I gave at the American Control Conference in June 4th, 2014 in Portland, Oregon. The presentation was on PID control using wireless measurements. If you're currently considering using a wireless measurement in closed loop control, then I hope you find this presentation of help as you address this. About 5 years ago, most of the major manufacturers of transmitters began to introduce wireless transmitters based upon the wireless heart specification. Since that time, the wireless heart specification has become an international IEC standard and is widely used within the industry. The wireless technology has been very much embraced by the process control industry. Many installations that initially installed wireless originally were only intending to use the measurement in a monitoring mode only. But having first-hand experience with the reliability of these transmitters, many plants now are looking at how to incorporate wireless measurement into control. As you investigate control using wireless measurement, you find there are a number of technical challenges, and we'll go through those today. It turns out that the PID can be modified to allow very effective control using wireless measurement. So we'll be talking about that modification, which is known as the PIDPlus. If you don't have PIDPlus within your distributed control system, then there are other ways to address wireless control. And we'll be looking at one of those in terms of using the PID, the traditional PID, with an observer to compensate for the fact that the measurement is not being updated each control execution. The two observers we'll be looking at are the Kalman Filter and Smith Predictor. We'll be looking at how those observers have to be modified to account for a wireless measurement. We'll then compare the PIDPlus performance with a wireless measurement to PID and a modified observer using a wireless measurement. In a traditional installation, you find that the rule of thumb is that the PID should be executed 4 to 10 times faster than the process response time. That is the process time constant plus process delay. In most DCSs, you'll find that the I/O is very oversample, that is, providing new measurements much faster than the control is executed. And the reason this is done is to minimize any delay between the measurement being in the control system and it being used in control. One of the underlying assumptions of the PID design is that each time the PID executes, there's a new measurement available, and also the fact that the PID is executed on a very periodic basis. These underlying assumptions are often violated then in terms of when you're using a wireless measurement, and therefore it's necessary to modify the PID or to have an alternate way of correcting for the fact the measurement is not available, and that can be done through an observer, as we'll see. The time frame in which in a traditional installation the information comes into the control system is shown on the bottom of this screen. The control update then is shown to occur at least 4 times over the process response time. If you were to set up your wireless measurement to try to emulate this, that is, to provide an update as fast as is normally provided within the DCS, you'd find you quickly burn out your battery. Realistically, to achieve a 5 to 7 year battery life, the wireless measurement will only be updated, say, over 15 or over 30 seconds in terms of periodically being communicated to the control system. Within the wireless heart specification, there is the option for manufacturers to use something called window communication to reduce the energy required to communicate new measurement value. With window communication, the transmitter wakes up periodically and does a measurement, but then it compares that measurement to the last communicated value, and only if that value exceeds a specified resolution limit is the value actually communicated. Also, if the last communication has between now and the last communication exceeds a refresh time, then it also will communicate the new value. So unless one of those two criteria are met, the new measurement is not updated. As a result, with window communication, you find that you get non-periodic update of your measurement coming into your control system. So in a wired environment, you'll find then that the measurement is updated much slower than in a traditional installation, and it may or may not be periodically updated as it comes into the control system. To correct for this and to compensate for this, then the PID may be modified, and with the PIDPlus, both the reset and the rate calculation within the PID are modified to handle wireless communication. In a traditional PID with a wired transmitter, normally the PID is implemented where the reset is created using a positive feedback network, as is shown here. With the PIDPlus, a whole circuit is provided after that filter in the positive feedback network, where the filtered output only is used with the proportional contribution when a new measurement comes in. So the last filtered value is maintained and is used in the control until a new measurement value comes in. In the meantime, the filter continues to reflect what is happening within the process. And in this way, then we can handle the fact that the measurement is not being updated each time the PID executes. When we implement wireless control, we recommend that the PIDPlus be executed much faster than the update in terms of communication of the new measurement. If you're using rate action, then the PIDPlus calculates the rate contribution in a special way as well, based upon the change in measurement from the last communicated value to the new communicated value, and the elapsed time in between communications. So in this way, then the PID has been modified to specifically address a wireless measurement. Now, the PIDPlus is only available in one commercial system today. So if you don't have that capability, then we wanted to explore and look at other ways you can address wireless control using a traditional PID, and the most straightforward way of doing that is to use an observer with your PID. In this presentation, will investigate two types of observers. One is the Kalman Filter, and the other is a Smith Predictor. When you're working with an observer, basically you're implementing a model of your process and then using that model in the control, and then in some way use your measurement to update the process model. The process model it can be implemented very easily within most DCS systems, as is shown here. It's fairly straightforward in terms of the calculation. Within your process, the model hopefully represents the dynamics and the gain associated with your process. In your running plant, you'll also have measurement and process noise. So this is specifically addressed within the Kalman Filter, where it's assumed you know the measurement and process noise and the covariance associated with those. And we'll see how this impacts the way we implement the Kalman Filter. In a Kalman Filter implementation using a wired transmitter, you notice then that the process model is the basis for the Kalman Filter. We compare the predicted value to the actual measured value to generate a residual, and then we multiply that by a gain known as the Kalman gain to correct the model for any difference between the model and what's happening in a process. And in the Kalman filter, this correction was mainly there to correct for measurement noise, but also is necessary to correct for unmeasured disturbances and inaccuracies in the model itself. It turns out that if we assume that the process and measurement noise are fairly constant in terms of the noise level, then the gain, Kalman gain, is a constant value. And in particular, if we assume that there is no measurement noise, then the Kalman gain is just 1 over h, where h is the scaling factor to account for the difference in engineering units between your manipulated parameter and your control parameter. So in most cases then, we'll assume then that the Kalman filter is just a tunable gain. When we look at the Kalman filter for use with a wireless measurement, we won't be having a new measurement each time the Kalman filter executes. To account for that, what we recommend is that the residual value be held between new measurement updates. That is, we only update the model when we have a new measurement where we can compare a predicted and measured value. And this is fairly effective in terms of handling then the wireless measurement when applying the Kalman filter. When we look at the Smith Predictor, this has been used widely within the process industry, mainly to address dead time dominant processes. Here we're using it just as an observer, where the technique for the model update is quite different than in the Kalman filter. You notice here that the difference between the model and the measured value is calculated as residual, and that is just added to the model to correct for any difference between the actual process and the calculated process using the model. When we're dealing with a wireless measurement, we won't have a new measurement coming in, which is traditionally what the Smith Predictor is designed for. So in that case, we again are recommending that the residual value be held between new measurement updates, and in this way the control is based upon your process model, and then you're correcting the model based upon comparison of predicted and actual value when you have new measurement updates. We wanted to then compare the PIDPlus performance using a wireless measurement to PID and observer with a wireless measurement. So we created a simulation environment in which the process gain was 1, process time constant 6, and dead time 2. The control, the PIDPlus, as well as the PID used with the observer were all tuned exactly the same for a lambda factor 1. That means the process gain was 1 over, or the controller gain was 1 over the process gain, and the reset was set equal to the process time constant plus process dead time. We assume that there is no noise in the measurement, and therefore the Kalman gain is just 1 over h, and since we're working both in the measurement and the output in terms of percent of scale, then the Kalman gain was just 1. To make things interesting here in the test, we used windowed communication for the wireless communication, where the windowed communication was configured for 1% change and 10% default period. That means the new measured value is only communicated if it changes by more than 1% from the last communicated value, or if the time since the last communicated value has exceeded 10 seconds. So this was then used for all of the tests that we did. The module execution was set at a half a second, much faster than the actual communication, which is what we always recommend to minimize any delay between the new measurement coming in and being used in control. This shows the comparison of PID with a wired measurement to PIDPlus with a wireless measurement, where we're introducing a set point change. You notice that in this case the response is very close between the wired installation with PID and the wireless with PIDPlus. We introduce a unmeasured disturbance at this point into the control. And you notice again the correction and bringing us back to set point is very much the same. There's a little bit of difference between the PIDPlus and the wired measurement, but nothing significant. When we get a new measurement coming in, we notice that the valve is immediately positioned to where the valve would have been if you'd had a wired installation. The difference between the control, as you can see graphically, is very little difference. And if we look at the interval of absolute error, again, very little difference between the two. However, there is a significant difference in the fact that with the wired installation, we use 456 new measurement values over this time frame, whereas with the wireless, with PIDPlus, we only use 43. So we reduced the number of new values used in control by over a factor of 10, and yet we provided the same quality of control using PIDPlus. When we look at the using the Kalman filter with the wireless measurement of traditional PID versus a wired installation, we notice that on a set point change, there's very similar response. Also, on an unmeasured disturbance being introduced, we notice that the control is very similar between the wired and the wireless. Where we have the model exactly set equal to the process, that is, there's no error at all, in this ideal world, then the actual performance is extremely close to the wired installation. It's actually a little bit better than the PIDPlus if we assume this ideal condition. For the Smith Predictor, we again see that on a set point change, that the wireless versus wired installation is very similar. On an unmeasured disturbance, we notice that there is a larger deviation from what the wired installation would provide in terms of recovery. And so the performance is a little worse than the PIDPlus in terms of looking at the interval of absolute error, but overall very good quality of control. So in summary, the PIDPlus is really the preferred way of addressing wireless control. It's very robust. Again, we recommend that it be executed much faster than the actual communicated value coming in to minimize any delay between the new measurement coming in and being used in control. It is available in the Delta V control system as a standard feature. If you don't have access to the PIDPlus, then using the traditional PID in your control system, you can match that up with an observer. It is necessary to modify the observer to correct for the fact that the new measurement is not available each time the control executes. The comparison between PIDPlus and the observer was one where the observer was ideal, that is, the model exactly matched the real process, and there was no process noise introduced. And so there's a need for further research on the use of the observer, and that's something that we encourage the participants at ACC to take on as a research project to further investigate the observer and its performance, where you have a model mismatch between the actual real installation and the assumed model, and where you have noise within the process. If you want to know more about wireless, I've done a number of papers on that, and some of those are shown here. So we hope some of these references will be of help to you. Again, I appreciate you taking the time to view this video, and hope the information has been of help to you.